I'm delighted to give the last talk in the series of virtual colloquia organized by the University of Art of Berlin and Studio Quantum. Thank you so much for having me. Let's get started, shall we? So today I want to tell you about the entangled marriage of art and quantum physics. So to give you a little bit more of a context about what we are doing, I'm the manager of the Yale Quantum Institute, which is one of the institutes created at Yale in the US on the East Coast between Boston and New York. And to give you a sense of the scale of the work, we have 26 faculty members that run research groups. So that's around 170 people on campus, a mix of students, both undergrads, graduate students, but also postdocs and researchers working in. We are well known for developing the field of circuit quantum electrodynamics, and we hosted a conference about a little bit less than a month ago in early January called Circuit QED at 20 to celebrate the 20th anniversary of that field. So this is a photo of, that was taken at the conference with a mix of Yale researchers, Yale alumni, and also people working in the field. But I think that the Yale quantum effort is way larger than this. These are all the research topic at Yale. Some of it that you can recognize, like the most famous one is superconductive qubits and circuits, and then we also work on quantum computer science, communication network, quantum sensor, quantum material, quantum cybersecurity, quantum chemistry, quantum photonics, quantum atom and molecular physics. There's really a large field of research at Yale. And so I know that you are now experts in quantum physics because you've been working in this all year long. But I want you to put your feet in somebody's shoes that doesn't know anything about quantum. And so when you see this kind of all of this research field, it may be a little bit scary. You may be shocked on this, but fear not, because I'm here to tell you that quantum physics is actually quite easy. It's not rocket science. And I know this because I am a former rocket scientist. And so to bring you up to speed, I think I want to start with our first chapter in this talk, what you bring to the table, and I want to talk about the emotional baggage in the field. So to give you some context about my background, so I'm a rocket scientist. I used to perform experiments in this zero-gravity plane that was run by ESA, CNES, and DLR in Germany. And I was studying the evolution of gravity on the evaporation of methanol, ethanol, and propanol, and all the other liquid. And so when you film them with the camera, infrared camera from the top, you can see this wave pattern ripple all around it. And so we were studying this and seeing how the different level of gravity would affect this. The goal was to try to figure out a way to better understand evaporative cooling, to see if we could do that on Mars, on the Moon, and in different part of space for travel and specification. And then I slowly moved to droplets, which had seeds in it, so nanoparticles, polymers, and all those things, and studying how all these components reacted in liquid metal and in under magnetic field. But all of this is to show you a case that I have a strong material science background, but not really so much of a quantum thing. However, when I've studied this, what I realized what passioned me the most was to build around me a community of scientists. I didn't care much to do the science myself, but it was fascinating to talk about it with these talented postdocs. And so when I joined Yale as a postdoc in 2014, what I realized that Yale did not have a Yale Postdoctoral Association. So with a handful of my colleagues, we built one where I was one of the co-founder. And then since it was really something that was really fun to run, the students and postdocs there are fascinating. And so building community and removing the burden of administration to these talented researchers was something that really fascinated me. And so when Yale created the Quantum Institute, I applied to the job of manager, and they basically rebuilt the floor where I'm currently located in, renovated completely it, and then gave me the key of a blank slate and a copy of the book Quantum Physics for Dummies. And I can tell you that much, is that this is not an easy book. When you start reading it, you feel, oh, quantum physics for dummies, maybe I could get behind this. But unfortunately, this is way more difficult than this. And you think when you're reading this, like, I must be worse than a dummy. And so that leads us to our second chapter in this talk today, about quantum, that mysterious stranger. So when you first want to learn about a topic, I don't know what you guys are doing, but what I did was I started Googling. So I Googled quantum, and this is one of the first images that comes into play. This is a blackboard with a lot of equation drawings, and this is supposed to be quantum. But when you look at this whiteboard, you have a light bulb, you have an atom, you have some circuit boards, you have some equation, you have of course the Einstein E equal mc squared, but then nothing is really quantum. It just gives you a sense of confusion. And so if you keep scrolling, you have this kind of visualization. So I assume this is two entangled bits with the magic electrical link representing entanglement, but it doesn't give you a sense of what it is. I think it brings more confusion to the equation. Now we have a cat with a lot of vectors and sphere and moving around, so the cat is probably a nod to Schrodinger's cat. But it doesn't help you. Like, I think it creates more of a sense of confusion. And if we keep scrolling, it's get even worse. Now we have people disintegrated in binary modes. We have like human having blue thoughts in their brain, like as if they could like think about this. And I think this is one of the challenges, that it's really hard to visualize quantum science. And so I think what we are left is visualization from artists and marketing teams that try to do something. And so it can go even very wrong. Now we have laser with people getting beamed and teleported everywhere. And if you keep scrolling, you end up with this quote of Richard Feynman that say, I think I can safely say that nobody understands quantum mechanics. And this gives a pass to everybody in the general public to say, okay, I've tried, I've Googled it, and now nobody understands. Why would I make the effort? And I think this is the challenge we're fighting against to do science outreach. It's a challenge because it is really, the quantum science is going to be really a new technology that will shift the market. It is predicted that by 2028, the global market will reach $53 billion. And so we really need to work together to try to help everybody in the general population to understand why there's so much involvement and investment of taxpayer money into this endeavor. Every little hubs has this own center. So we are part of Quantum City in Connecticut, but I know that Chicago has also a quantum exchange. CQA, the DL from in Germany has the quantum computing initiatives, and then there's a lot of them in Europe. We have the quantum flagship, the quantum industry in Canada, the national quantum safe network for Singapore. I try to match the number of quantum initiatives with the number of Goethe Institute location, but it's quite a lot. So I think the Goethe Institute is really winning the fight on this. But we're getting there. I want to have a special mention to the island government that has the best tagline of all of them with their Quantum 2030 initiatives, putting Ireland in a quantum superposition. Like, brilliant marketing job on this one. Very jealous I didn't come up with it. And so in all of these initiatives, the limiting factor is going to be the workforce development. So we need really to have people who care, learn, and be excited about what we do. And I think this is what we're trying to do with Quantum City in the Volkswagen development. Chapter 3. Getting to know quantum. So if you pass the first initial shock of the being scared of quantum, you start to find images like this. So this is one of the IBM quantum computers, and you can see these Apple-looking computers. And so it's a beautiful, well-made machine. The issue is that I think it gives a false impression to the general public that quantum physics is just engineering and product now. I think we are still very much in the phase of research and development. And to give you another look at a quantum computer and quantum devices, this is what our lab looks like. So there's two options. Either we are way more messier than IBM, which could be a thing, but also I think it really, the IBM photo really hide the fact that people are still actively working on this and we don't know how this thing works, like to make them more capable of performing classical computer. And so this is some dilution fridges photos that we have in our labs, and this is where all the bits and qubits, for example, performing the quantum computation are located in. So this is our tiny substrate, and they're placed in cavity by our researcher. So what I want to convey to you by sharing these photos is that this technology is pretty much involved with human. Like we have, from all the previous images, seen that, oh, it's this blue, almost like a goddess aura of things, but it's actually pretty much researcher tinkering with the machine. So it's something that's very important to remember. And so we have some example of what a full devices can look like when it's closed and cooled down to absolute zero. We try to organize tours of our labs, but I think it's something that is only limited to the local population. Like, for example, this was during a conference, we hosted tours, but it's not something we can bring a lot of people in. So we need to find another way to bring the science outside of the lab and bring them to where the public is. Because that's something we've started doing. I hosted, when I started working at YQI, some science outreach events that were widely popular. We have here Bill Phillips, who was a Nobel Prize laureate, talking about the coolest things in science. And we have liquid nitrogen. He did a lot of cool tricks. But the issue here is that the people who are interested in these talks are already involved in science. It's something that they already do. How do you bring people who are not considering STEM at all and thinks that it's too hard for them? So for that, I've partnered with the Yale library, the Yale Bass Library, and curated a collection of books called From DOS to Qiskit, DOS being the old operating system of classical computer, and Qiskit one of the many languages that are being used for quantum computation, and curated for the library a collection of books with different angles you can discover quantum with. So the first one was if you have a very academic mindset, we have some teaching books of quantum theory, but we also have some with a lot of pop culture involved. Like if you're interested in more learning about how we could use and how we can imagine the future with these machines. We also have one about the angle of history, if you want to learn about the science through the discovery process of the founding father and scientist of the era. So people can look through and enter this field to the angle they're interested in. But we also combine this collection with a lot of artifacts of quantum devices that we had in the lab that were decommissioned and mix them and match, so to give you an idea of what a quantum computer looks like. And one thing that's interesting, and I particularly like this photo, is the smile on people's faces. In the past, when I was talking about quantum physics to my friends, I usually have, like when I say I work in quantum physics, people open wide eyes, blank stare, and slowly back up. It's like, oh, that sounds really, really hard. I don't want to talk about it. And I think by bringing this outside of the lab and showing them simple components, I think it showcases how fun this field can be, and I think it removes some of the phobia. And I think this is really a good thing that I really appreciate, like mixing joy of learning with this. And to do that, you can do a handful of things. You can make jokes, but you can also use some of the cool books that we have. So, for example, this is Chris Perry's book, Quantum Physics for Babies, that you can bring to any newborn that you find. It could be a sister, it could be a sibling, it could be a friend, and then really start teaching them about quantum physics. This one is a really fun book. I highly recommend. It's four or 5 pages, so quick read. Chapter 3, On a Date with Art. This is where we're getting to the depth of the subject here. So one thing we did at YQI to try to bring a little bit of quantum physics outside is, in addition to your technical talk series, seminar series, I started hosting a series in collaboration with the Frankie program in Science and the Humanities that mix art and science. So we had about, like some example of these talks were about quantum physics and something else. For example, Michael Berry from the University of Bristol talked about how quantum physics democratized music, and that was one of the first talk we hosted in 2017. He taught us about how the research and development of quantum technology led to laser improvement, compact disc, and then all this medium that were used to play music in the room. So that was a very fascinating thing, and the public really reacted very well. It was a general talk, and people were like, "Oh, interested in the music and the state for the quantum physics." We also had the quantum physicist Stephen Alexander talking about a bit of the theory of the black universe and also jazz and physics. We had Karen Barad, who I know gave a talk in the Goethe series a little bit earlier, and told us about spooky objects and the particle wave duality nature of light. And recently we had Clem Jankiewicz, who told us about coding quantum computers without doing coding, so like working on graphic interface and doing all those things. And really, this really connected well with the public. People, I think, are interested in learning about quantum physics, but they need a little bit of help. And I think using art and the humanities as a hook to teach these complex topics is really a nice way to put it. And so, of course, we extended this series, which is one of my favorite series ever, if I do say so myself, where we mixed really a lot of topics, expanding to just not quantum physics, but all STEM. We had quantum literature, we had music and architecture, we had literature and murder mystery and quantum technology, art and science, biology, physics and dance, mathematics and crochet, and it was really a fascinating thing. And so here are some of the images. So this was the conversation about physics and dance with Sarah Demers and Emily Kurt. And then we had Diana Tamina from Cornell telling us about crocheting this coral-looking sculpture with yarn to explain hyperbolic plane, which is this very complex mathematical concept, and that's often hard to visualize, and so students could see this. And so we had people from the Yarn Barn, which is a store, a art and craft store, that came in and talked about mathematics. And so I think that's the approach that we want to do with this. For example, we had Stuart Smith talking about graphic design for quantum researcher and helping them design better and more effective communication tools for the work they're doing. Here's Karen Barad. We worked with students at the School of Architecture and built them a portable suitcase where they could run the Young experiments, the double slit experiments. So they were very happy with the suitcase, and so now when they go to conferences, they can bring around the suitcase and showcase that to the public. And this one was one of the most recent talk with Jen, talking about the artifacts. Talking about graphic design for quantum coding. And truly, this led to a lot of workshop. So, for example, this one is the artist Martha Lewis, working on color theory to help quantum researcher work on plots and making sure that what you convey with color is also what you want to match with the science. And so really, after all of this dating around, I think we had to be serious about quantum and art. And for chapter 4, we're going to the proposal. Remember the blank space that I was mentioning earlier at YQI? Well, I wanted to have a visual. I wanted to have something that was visually striking, but also meaningful to researcher. And so a lot of people thought like, oh, we could have plot, we could have poster, we could have covers, but I think I wanted to have something that it's more in the realm of art than just pure science. And so working with Martha Lewis, she had in her practice this series called Brains, which is a series of crumpled paper where she drew trough and valley on the paper and on this. And so you could see here that she presented the work, and people were very excited about this because it's an interesting representation of something called quantum vacuum, where you have this trough and valley and minima and maxima in some of the parameter, but at the end of the day, if you do the average of all this value, it's just null. And so basically it's like your crumpled paper, you have trough valley, but then when you flatten the paper, everything becomes average, everything becomes zero. And so this became the mural that we have at YQI talking about the quantum fluctuation. And so all of the piece, this piece, and you'll see in the near few slides, that most of the work here that we do with art and science is a metaphorical representation of a key concept. And so this one is about quantum mechanical vacuum, as I said, and which every field undergoes random fluctuation, vibration, like you will have crumpled paper, but then it just become a null value if you add on all the scales and time. And so we knew from that very successful work that we had to do more. And so chapter 5 is the marriage. I immediately hired Martha Lewis as our inaugural artist in residence in early 2017. And by the summer 2018, she was working with Michel Devory, one of our faculty members, and quantum physicist Stefan Krastanov on an installation called I'll Be Your Qubit. So this installation took over the space at YQI. We get rid of all the chairs in our seminar room and had this installation that represents a dilution fridge, at least a metaphorical version of a fridge. You have this silk curtain coming in around, and inside you had a lot of sensor triggered by the walk of the visitors in this. And so this installation was part of the Arts and Idea Festival and came along with a series of talks trying to explain the entanglement of physics and art, and also like what was behind this. So we had about 300 people coming to the installation by a small group of 10, and they were interacting with all the elements of the sculpture. You can see on top of the ceiling, you have these LED strips. We had a webcam tracking the position of all the attendees, and then performing a quantum simulation based on this. Now we also had these flip boxes that we had with little sensor that you can see it's the white little dot that was triggered by people working by it. And so this piece was a play on the supervision of states, because you could use persistence of vision to allow to see one or more images, even if they are located on different sizes, impossible to see on at the same time. But that was the idea. And so for chapter 6, let's now talk about the entangled marriage. Our second artist in residence was Spencer Topel. We worked with him. He's a sound artist and was using scientific instruments to make music. He worked with Carl Saniak and Luc Burkhardt, two grad students at the time who are now full-fledged quantum physicists on sonification of instruments. So we went in the lab and listened to what we could, and it was very interesting to see what we could do. The initial goal was to try to see if we could listen to data and if we were able to detect by ear the error in the data and see if we could give an additional tool to scientists to work on this. So there was like this goal was to try to help with art and with sonification tools the science behind it. But we worked really on the walking the line between fine art and science, and so I think this is very important in our program. And so this is an artistic representation of the jump of electron between four states, and you can actually hear that in quantum sound. I'll get to that in a second. So we presented our work of sonification and trying to figure out how to use quantum computers for sonification to the crowd of researchers, and we had a lot of conversation about making sure that we did not use white noise as the component, but really quantum data, because you can pretty much plug any headphones to pretty much anything that has electricity in it and you can hear something. But we had a lot of conversation about making sure that what we were hearing was an actual data coming from quantum computers and not just random noise. And this work led to a full live concert for the Arts and Idea Festival in New Haven at Firehouse 12. And so I'm gonna show you a small snippet of the music video we filmed at Yale Inno Labs, so we can share with the public who were not at the concert. And so if you want to listen to the whole album, it's available on every streaming platform at Quantum Sound. Fair warning, the first review came in from my mother, who tried to listen it on Spotify and was complaining that Spotify was broken because it was only hissing noise. And I say, Mom, this is not Spotify that's broken, but it's our album. It's electronic music, experimental electronic music. So fair warning. But I think from a crowd of artists, Berlin artists, I think that might be your audience, and you might enjoy listening to it. And always, I was talking about the fact that we were trying to do science outreach through art, and what more could we do than force people in the street and watch this? So we, for the release of the album, we did a synchronized light show on the facade of the building of the YQI, and had people in the street listening to the show and seeing the space, and all was synced with the music, and so very highly visible. And so I'm sure this is some sort of guerrilla marketing where we came in and people walking by was like, oh, what's up with this light show everywhere? And so we were able to talk about quantum sound and the music and the science behind it. And so some more X-ray, more photos of the building. And then again, what I'm interested in is like the smile of people after this kind of events. They were very excited. Either they loved it or not, but at least it was something different that like touched them. And so what I hope is after this, they were like, oh, I wonder if I can learn a bit more about what they were doing. And I think this is truly the goal. But you must be wondering, why is it so entangled? And actually, for this piece, we went full circle. We went from science doing art to doing science again, because the work we've been doing here was really based on the fundamental work that Carl Soniak and Luc Burkhardt were doing with FRGs and studying the non-equilibrium quasi-particle in superconductive qubit. And so what was interesting is that we could listen to the different change, the different jump between a qubit in the ground state and excited state, if it was even or odd. And so you had basically 4 tones to play with in the composition. Same thing with the work that Luc Burkhardt did. He was studying error-detected networking for 3D circuits in quantum electrodynamics. And one thing that was very interesting is that he was able to create 2 signals that had a leader and then another signal that was just following the path. And so you could decide if it was a good follower or a bad follower. But the thing that was interesting is that you can actually use that type of entanglement and breaking it to generate a type of signal like a synthesizer. And so all of this complex performance was like during the performance, we had a quantum computer that was controlled live by Luke, one by Kyle, and then all of the signal were processed. The data was turned into a live processing and performed live. And so we had data from the previous experiment that Spencer was also doing, and all of this was mixed into a final sound, like 3 instruments. And so we sent that to the speaker, and at the same time we would broadcast it live on the radio at WDKN, and we had the recording for the album. And the thing that was interesting is that we basically built a simple quantum music synthesizer where you have quantum data that is downsample, and then mixing different logical gate and phase modulation, you could mix that into an audio signal output, so you can use that. And so basically all the tools that were created here were like the pedal that you can see in some of the concerts to make some effect on music. You could have the ground state, the 4-state operation to move in. You can have like this very long drawn transition from excited state to ground state to create a drone. And then we had pattern generation with the feedback sweep. And so all of this was published into the chapter of Quantum Computer Music, which is edited by Eduardo Miranda, who gave the talk last week. And so if you're interested in learning more about the tool behind this, I recommend reading this. And so this is where we had the entangled moment, going from science to art and to science again. So that's pretty exciting. I feel that it's very rewarding as a producer to have this happen. The book and all the work were released a little bit more than a year ago at one of the Goethe events in London at the institute there about quantum music computing. And so, as I told you, all of the work we've been doing is about metaphorical concept, and there's always a moment when the metaphor falls apart, because, of course, we are in the classical world, and quantum rules do not apply. And so this is the moment in my talk where this is happening to us. So I'm not going to pretend anymore that the entangled marriage still works, and so we're going to move to a different title, museum show. So we built a quantum revolution museum show to try to explain to the public what does quantum technology look like. And so we had the show at the New Haven Museum that had a composition with some artifacts of the labs, but also art and drawings from Martha Lewis in the thing. So it was a mix of what we had in the lab and what you could see in the lab, like a really engaging structure for the show. A lot of people were excited with the tracking lights, and I think it gave them a little bit of a concept of what quantum technology looks like, at least superconductive qubits in that case. And so next time when the media and the radio talks about quantum computing, we will have people will have this, oh, remember that was the show that I saw at that museum. A lot of interesting and important things, and so that's also what we want to see in this activity. I want to tell you a little bit more about, in this new chapter, about the human scale quantum equation we did this summer with our third artist in residence. So we had Stuart Smith, who is a technologist, and we worked with him on quantum equation. We built this bespoke light pole beacons we had that had a light sensor, and so basically when people were walking around it, it will trigger. So the sensor will see the motion of people, and it will trigger some error. So we use the flow of visitors as the proxy for error in a system, and then we had an algorithm that was correcting it. So you can see that it started green, and then the color changed, and as soon as it became blue, the algorithm fixed the error caused by the people walking. And so it was a work made in collaboration with a quantum researcher, Hugh, and so we worked on this and had that on campus twice. Once in the New Haven Green for the Arts and Idea, and then one at Loose Hall to make sure that the students are back for class during the semester. So this one is during the day at Loose Hall, and then you can see another version of it where we have people triggering the error by standing next to that. So the red pole are the qubits that have errors, and so the algorithm will correct that on the right. And so you have an idea of how this works. You basically do near pattern error correction, and so you try to find as quickly as possible in real-time error correction on the circuit of the balls. And so that's one of the images on the neon green. And I want to finish this with a preview of our upcoming work, so thamCATrope. So thamCATrope is an art app. It's a metaphorical quantum search in New Haven where you lose your cat and you go on campus and in the street of New Haven to try to look for it. In the meantime, when you look for this, you go into these scenes that are very grounded into classical physics. We designed them to look like old postcards that have been bleached by the sun, and then when you click on some of the info tools, you have some information on this. So it's basically a tour of New Haven with bits and pieces about entanglement, quantum computing, speed up, and all of these things. And so this is, for example, the Yale Quantum Institute, and you look for your cat, and so when you find it, it will try to offer you to go into a search using quantum computer to be more effective. And so instead of going in a binary search left and right, you go into this network entanglement of search, and so you can see all the location at once, and you can find the cat pretty easily. The application will be launching around May 2024, so we'll have that to going on. And so for all of the work that I told you about and all the art, you can visit arts.quantuminstitute.yale.edu, and you have all the information about what we've been doing, but also the science between us. Chapter 10, it is now your turn to recreate. We're going to use my metaphor once more. So let's have a polyamorous relationship with quantum and art, and it's going to be your turn to create. So what I can propose to you is that we're going to go into the mirror board, and we're going to split you all into 4 different themes. And what I want you to do is to have your art collective brainstorm ideas to create artwork, or at least ideas to start thinking about this, to underline a theme. So I'll put the link in the chat, and then we will split up in different breakout sessions so you can talk with this. I will talk to all of you. I will change rooms, then we can work on that. So the 4 themes are, so theme 1 is entanglement. So the quantum entanglement is a phenomenon that occurs when two systems with 2 particles are entangled. You do an operation, and then even if you move them far apart, when you look at one, the other one will be linked. And so this is what was referred as spooky action as a distance by Einstein, but this is something really real that has been done with satellites and laser from Earth. So we could do that from very far distances. So it's something that might be interesting for the art. So that's theme 1. Theme 2 is the concept of superposition. It means that in a classical system, you have often a binary system. So, like, for example, think about a light switch, up and down, like a binary code, 0 and 1. But a qubit is a quantum system, a quantum bit that can be in every position at the same time. So it could be 0 and 1, but also everything in between. So it's something that can be very interesting, and that we could use art to try to wrap a classical brain around this. Theme 3 is the observer effect. So we talked a little bit about this with the installation I'll be your qubit. It's the fact that when you observe, you disturb the system you observe. So a very classical concept is, for example, if you want to read the pressure, or measure the pressure of a tire on your car, your bike, you have to put a sensor in it, and you hear a little psst, and then you have some pressure leaving. So what you're measuring has been already changed by the fact that you're trying to observe it. But in quantum physics, it's even worse than this, because if you project your system, so often quantum systems are represented on an arrow on a sphere going like 360 in every direction. And so if you measure that through the x or the y-axis, the system will give you a value that is not necessarily correct based on your axis of measurement. So basically the observation change irreversibly the value that you're going. So that's something that could be very interesting also, as well as a theme. And the last and final theme is the wave-particle duality. So we can see our good friend Karen Barad again talking about this during their talk. And it's the idea is that if you shoot a laser through splits, you can either have it be a particle, a point, or you could have a pattern of waves. And there's a lot of interference pattern that could be very interesting as a way to create art. So I will stop here and make you go onto the mirror board, and we'll break out in the session here. Thank you all for sharing your ideas, and it was very interesting to see your take on all of these themes. I hope you had a great time, and there's one last thing that I want to say is that for the last chapter, chapter 11, I want you to go into the world and try to share with the world what you're creating using quantum and science, and having all this being a full and encompassing practice to make sure that it's relevant to you, to your practice, you're happy with what you're creating, but also if it can give the inspiration for people to learn about quantum physics, that would be delightful. So on this, I hope you will live happily ever after. Thank you very much.